Okay, it's 5 p.m. here in Germany. Hello, everyone, and a very warm welcome from my side to everyone joining our webinar today. My name is Mohammed, and it's a pleasure for me to discuss with you the kinetics analysis of pyrolysis. Before we dive into the presentation, I would like to give you a brief introduction. Today's webinar will be recorded, and you will receive the video by email within a few days. Of course, you will have also the opportunity to ask your questions. In your Microsoft Teams windows, you should find the Q&A section somewhere at the top on the right. The icon looks like a speech bubble with a question mark. I will answer question at the end of this webinar. If I cannot cover all of them, I will follow up by email, so please include your email with your questions so we can get back to you. If you have any other questions, you are also welcome to contact us at any time at our general webinar address, webinar_ngp@netsh.com. I have already posted in the chat so you can get access at any time. So just few words about the NETSH Group. For those joining us for the first time, the NETSH Group is a family-owned company established in the early 1870s in Zelb, in the north of Bavaria region in Germany, so more than 150 years right now. We have three different business units. We came from the analyzing and testing business unit, which specialize in the design and manufacture of instruments for thermal analysis, rheology, and fire testing. And we have also another two business units, grinding and dispersing. This business unit specializes in the design and manufacture of equipment for wet and dry grinding, mixing, dispersing, and other related applications. And finally, the pumps and systems unit, which specializes in the design and manufacture of the right positive displacements pump for your application. So within the business units analyzing and testing, we have a wide range of products and services covering a wide temperature range from -260 up to 2800 degrees C. So we manufacture instruments for thermal analysis and thermal physical properties testing, for example, determination of thermal conductivity, and instruments like accelerating rate calorimetry for looking in adiabatic situation. And we have also equipment for determining the reaction to fire material in line with international standards. And finally, we have rheological testing methods to measure the non-Newtonian liquids and soft solids. Within the NETSH Group, we have more than 4,700 employees and more than 700 employees within the analyzing and testing unit, and we turn over more than 150 million euro per year. In NETSH analyzing and testing units, we have laboratories and sales and services location worldwide, and we have production sites mainly in Europe, but also in Asia as well. And also we have offices across North America, South America, and finally Sydney, Australia. I hope that this gives you a picture where we are based. So my agenda will start with an overview of pyrolysis. Then I will discuss the kinetics in solids. It's a quick overview about the fundamental and Arrhenius equation. And then we will speak about the kinetics parameters, mainly activation energy and pre-exponential factor. After that, I will introduce the Kinetics Neo software as a tool which can save for your time and accurately determine the kinetics parameters. So pyrolysis is the thermal decomposition of organic material in the absence of oxygen. It's the key process in converting biomass or waste material into a useful product like bio-oil or syngas. And for that, most used materials that the biomass, which I will show you a case study in my presentation. It's specifically about olive stone, and then the plastic or thermoplastic, which I will show you as a demonstration with the Kinetics Neo software, and the rubber as a third material. And here you can see the workflow that we need thermogravimetric analysis to see the mass change, and after that we can do the kinetics analysis in order to determine the kinetics parameters. So the current challenge in the industrial application of pyrolysis kinetics. So the first one is the poor choice of kinetics methods and the experimental condition, which we will speak about that later on, and also the kinetics complexity of the multi-step pyrolysis process. Well, kinetics has basically two aspects, mainly to better understand the mechanism of a chemical reaction and to also describe this experimental data with a mathematical model that fits with the experimental data. And then, secondly, we are using this mathematical model to predict the behavior of material in time temperature, which is not easy or impossible to access. And now I will take my pen. So when we are speaking about kinetics, the first thing that comes to mind is the Arrhenius equation as the fundamental chemical kinetics. But let's start with the general equation. So the general equation is the first derivative of conversion over the time, and the conversion alpha, it means the reaction progress, or in our case in the pyrolysis, it's normalized measure of how much of your sample has decomposed during the decomposition. Then it's equal the Arrhenius dependence multiplied by the reaction model. And as we are speaking about pyrolysis, so the most used model, it's the first order, second order, and the n order. Then we have the Arrhenius equation, which equal the A as pre-exponential factor, and which we are calling it also the frequency factor, which represent the frequency of collision between reactant molecules. Then exponential of minus activation energy, and the activation energy, it's the energy what it need a reactant, A, for example, in order to transform to be as a product. It's the minimum energy what it needs. And divided by R, which is a gas constant, and T, the absolute temperature T by Kelvin. So how we can do the measurement for kinetics, and what kind of how many heating rates we need and what kind of heating rates exactly. So for us in Netch, that we are using a sample for 10 milligram, and for the heating rates we need at least 3 measurements at different heating rates with the R squared value greater than 0.995. The R squared, it's the coefficient of determination, which giving us an idea about the goodness of the fit. If it's less than 0.995, so in this case, we recommend the customer or the professor or student who are doing kinetics to make more heating rate in order to increase the accuracy of the model. And for pyrolysis, the most reported heating rate, it's 1, 2, 5, 10, and 20 K per minute. And also we strongly advise that to repeat each measurement at least once. So how we can calculate the conversion from the measurement data? So in this case, we have a TG data, the mass loss, and we are assuming that here that we have A as a reactant and B as a product, and we can calculate the conversion, which equal the ratio of the partial mass divided by the total mass. And the partial mass you can calculate it by the initial mass minus the mass at the T, or at the time, or at the temperature, divided by the initial mass minus the final mass. And for the conversion, it's between 0 and 1, and also you can, some in the letter they are preferring to use between 0 and 100%. So why we need Kinetics Neo software? So Kinetics Neo software, it's only a tool which we are using it in order to save time and the trial error approach. So basically in our software, it's covering all methods and the mathematical equation which can help you to describe your experimental data. And then we can determine quickly the activation energy, pre-exponential factor, and the reaction model, which we are calling it also the kinetics triplet. And then by Kinetics Neo software, and based on the most suitable model, that we can go further and do the prediction and also the process optimization. And here you can see the workflow for our kinetics, that we need a data type. In this case, as we are speaking about pyrolysis, that we need TGA data, and we will import them into Kinetics Neo software. And we can do kinetics analysis by two approach. We have the first one is the model based or the model free, and the model free is the most used in the literature, as it's contain the all famous method and equation like Friedman and Ozawa and other ones. And then we can do the prediction and process optimization. So we would like to do pyrolysis, but what kind of measurement we can do? So basically, Kinetics Neo software generally support the data from dielectric analysis, dilatometer, arc, rheology measurement, dynamical mechanical analysis, DSC, and TGA, as we are speaking for pyrolysis. Also, Kinetics Neo software can support the data from niche and non-niche instrument. And regarding the file, it can be text file or CSV. Also, what we need exactly? We need only data columns, 3 columns, temperature, time, signal at any order. So here it's a screenshot from our software, which I will show you later on during the demonstration. That here on the top in the x-axis that we have temperature, time, and log of the time, and then in the y-axis we have signal. In this case, as you can see, that we have the mass loss by percentage, conversion, and the conversion rate, which is the first derivative of conversion over time, and then the concentration, reaction rate, and also the sum of the peaks. So here in the data import, you can see them under the source data. As you can see here, we have 4 files, and you can see here under the legend that 1K per minute, 2K per minute, 5K, and 10K per minute, the different heating rates. Then we have kinetics analysis that for the single point, and this method we are often used for a quick estimation or when the data are at the full range of conversion, it's not available. So this is one of the methods which align with ESTM international standards. And then we have the ISO conversional model free. So this one, which I said already before, that this one is the most used in the literature, the Friedman, the Ozawa Flynn, Wall, and Kissinger Akahira Sonos. And then we have the model-based kinetics, that if you know exactly the mechanism of your decomposition. So in this case, we have more than 20 type of reaction, and you can easily assign for each one for each single step. Then we have the model design, which we can also describe the model if we have consecutive reaction or competing or independent. For this part, I will speak later on in the next slide. Then here under the parameters, you can see here clearly the activation energy, the log pre-exponential factor, the reaction order, and the contribution. And here I would like just to tell you what we are speaking by the contribution. So as you can see here that we have for this one, the contribution is 0.73, and it's for the B, for the steps which is B goes to C, and we can see here clearly that for this step it's almost 2/3, so that's why the contribution it's equal this for this step. Then we have the manual optimization, that which will help us during the optimization for the model, then the automatic one, and after that we have a statistical comparison, which the most of the PhD student and professor, when they would like to do good publication, they will prefer to make a comparison and use the different model, and after that choose which one is the best one. Then we have the prediction and the process optimization. So here, as you can see, that we have the connection between the steps, and for the first one, it's independent. When we in the reactant and the product are not involved in the other steps, and also when you know that it's a mixture, no interacting compound, so in this case you can select that one in the software at an independent step. Also consecutive, so in this case, as you can see in this example, it's clearly we can tell that it's consecutive, that we have here at the beginning we consider as A goes to B in this part, and after that goes to C. And for competing, that we see that the mass loss, it's not ending at the same time with the same percentage, which we are assuming that here we have two different product, A give us B and give us C, and we can describe it by this way. Then, when we are speaking about the coefficient of determination, so as we know that when the R squared it's equal what, so we can say that we have a perfect fit, and when the R squared it's less than 0.995, we can consider it as a poor fit, and in this case we try to optimize and also to add more Hayton rate in order to increase the accuracy of the model. And here we have a TGA result, and we used both of them model free, but with different method. The first one, it was Friedman, and the second one, Kissinger, Akahira, Sonod. And we can see that for the highest R squared, when we have 0.999, that the fit and the experimental data are in agreement together. And we see the other side, when we have the R squared, it's less than 0.995, so it's clearly you can see that the fit with the experimental data are not in agreement. For the fit, it's the solid line, and for the dot, it's the experimental data. Here we have also the curve visualization fitting. So why it's important? We need the visualization of the fit, because in many studies we saw recently that they are mentioning only the R squared, and the R squared it's not always giving us the whole story. So that's why I choose a case when we have both of them. The R squared it's 0.99 with the high R squared, but which one we can choose. So in this case, we need the visualization fitting in order to select which one is the best. And as you can see here, that for this model, it's not the most suitable. So that's why in this case, we will choose the Friedman model. And now I will speak about our case study. So it was done as application note under the title Unlocking the Pyrolysis of Olive Stone Biomass, TGA Analysis and the Appropriate Kinetic Approach. So you can, if you can Google it, you can find it directly. And also if you would like to go to the niche website, and you will find it under the application section. So the reason why we select olive stone, because they contain carbon-based compounds like cellulose, hemicellulose, and lignin. And the challenge with the olive stone is their complex composition. They are heterogeneous and making it difficult to determine the kinetics because of their decomposition stage overlap. And in this figure, it's showing us the TGA and the first derivative of it, of the olive stone at different heating rates. and you can see it's 2.5, 5, 7, 10, 20, 30, and 40. And here we used the TG309 Libra as instrument from Niche in order to do this measurement. And you can see that for the condition that we use alumina open crucible and simple mass, it was in the range between 9.65 milligram to 9.85 milligram. And for the temperature range, it was between 25 degrees C to 1000 degrees C. And the atmosphere, it was under nitrogen, 40 milliliter per minute. And after that, it switched to synthetic air at 900 degrees C. And that's why from here you will see in the curve I did not take in consideration between 900 and 1000, and as you know that the pyrolysis it's only done in the absence of oxygen. So here, as you can see also that here we have the first mass loss, which corresponds to 3.3% mass loss moisture evaporation. So the first step is to do the thermal stability, but we can do more, yes, right now by Kinetics Neo software, that we can do more. Now, those results, what we are seeing now, it's the decomposition of olive stone to 900 degrees C at different heating rate, and which has been done by the TGA. And we can see here clearly that when we are increasing the heating rates, we saw the effect or the influence of the heating rate when the curve is shift to the higher temperature. And also here for this mass loss 3.3 evaporation, that we will not take it in consideration during the kinetics analysis. Then how to determine the number of the steps. So here, in order to determine the number of steps that we are doing the kinetics analysis, and the first thing that we are changing from the signal to the conversion, and we are selecting the slowest heating rate, which giving us more information. And as you can see that here we have the conversion rate versus the temperature, and we have 4 shoulder and 1 main peak. The first one, it was around 198 degrees C, then the second one 260 degrees C, then 306 degrees C, and after that we have another shoulder at 340 degrees C, and the last one is around 384 degrees C. So now we can see that we are going to assume that we have 5 steps, which showing us the different decomposition steps of olive stone. And then we double check in the literature, and we realized that it's true, and we found that for the first one for the first step it belongs to hemicellulose. It's the early decomposition of it. Then we have the main decomposition of hemicellulose. So in this case, if we take only the kinetics analysis of hemicellulose, that we will find 2 steps of it. Then we found the cellulose as the main peak, and then the late decomposition of it, and then the final one is the lignin. For more information about that, you can find it, as I said before, under our application note, unlocking the pyrolysis of olive stone biomass, TGA analysis, and the appropriate kinetic approach. And here, this is one of the methods when we try to describe perfectly our model, that we can assign for each step a single reaction type. And as you can see that here we have A goes to B, and B goes to C, and C goes to D, and D goes to A, and F go to G. So then after that, we have the option to do the sum of the peaks, which is the green dark, we can say, and you can see here clearly how it's the fit. It's in perfect agreement with the experimental data. Then after that, we change from the conversion rate to the signal, and we click on optimize. And here now we found the most suitable model for our decomposition or pyrolysis of olive stone. And here I will zoom in order to see the goodness of the fit. And then we can, after selecting the most suitable model. So the second part is to extract the different kinetics parameters, the activation energy, the log per exponential factor, the reaction order, and the contribution. And here, as you can see, that it's the coefficient of determination which showing us the goodness of the fit. Also, another important things that, as you remember, that the main peak belongs to the cellulose, which is C goes to D, and on the last one it's D goes to. So if we say here the contribution or the total contribution, it's around 0.32 or 33. So in this case, that only by using kinetics analysis we can tell you that the contribution or the composition of the olive stone, it's 33% of cellulose. And also after that, we can tell you that because the first two, it belongs to hemicellulose, that we can tell you 34% of hemicellulose, and the other things, it belongs to the lignin. Yes, for sure, there is a possibility to get a confirmation by another analytical method, like HTIR or mass spectroscopy, but also you can start with the other methods and to get a validation from the kinetics analysis. Then we can do the process optimization, or what we are calling it the conversion control. So here I have two figures. The first one, it's at conversion of 5% per minute, and the second one at conversion of 1% per minute. And in this case, it's clearly, you can see by conversion of 1%, it will be slower and much longer. It's around 118 minutes in this part. And the second one, when we have a conversion or fast conversion, that we can reach around 38 or 37 minutes. And here in the graph that you can see here, we have a mass loss, the time, and also the temperature. For the dash line, it's temperature, and for the solid one, it's the conversion. And then we can do the isothermal prediction. So this isothermal are both the same in terms of temperature isothermal and the time. The only difference is about here we have a signal with the mass loss by percent, and here we have the conversion. The idea for this one that even we can choose the most suitable model. It's based on the R-squared and also of the visualization of the fitting. That always we are asking the customer to make a kind of confirmation. That, for example, he will come, for example, for 300 degrees C for that one. And in this case, that he has to get like 10 milligram again of the olive stone and do isothermal by TGA, and after that to make a comparison and to validate if our model is 100% it's perfect or it needs some adjustment. Then we have the multi-step prediction. The multi-step prediction, it means that we have the possibility to change our temperature program, that we can do a different heating rate, like in this case 5-2, and a different isothermal versus the time. So in this case, I choose the case that we have between 10 and 400 degrees C for 5K per minute. After that, between 460 degrees C up to 900 degrees C by 2K per minute, and then the last one isothermal 900 for 150 minutes. And as you can see here, that we have 5. Sorry. Then we have the slow one, and after that we have the isothermal. And that one you can see, this is the mass loss versus the time with the new temperature program. And now I will take my software in order to show you a case study. But in this case, it's not for the biomass, but for a thermoplastic, for a polymer. And now I have already imported data under the under the first data. It's fine. You can see that we have 6 file which belong to the different heating rate 0.31, 3, 5, and 10. And we have the possibility here to also to increase the thickness. Of our curve, that sometimes some students would like to make a good publication and would like to the curve to show clearly in their articles. And now we can go to do the kinetics analysis. So the first step, I will go to the model base. And here, as I said before, that we are assuming that here we have A as a referent. And then we have B as a product. And then we are assuming that we have here C. A goes to B and B goes to C. So in this case, we have a kind of consecutive steps. I will click on it. And we have here 2 reaction steps with N order reaction. And why I choose the N order reaction, because the most used one in the pyrolysis for the decomposition of biomass, it's for the biomass material, it's N order reaction. Here we have also the possibility to name the project. And after that, we will click from the signal, we will change to the conversion rate for the y-axis. And then I will select only one heating rate. And now I will use the zoom function. And as you can see here, the solid line is we have 2 peaks, and the point, it's 2 peaks, but they are not on the right position. So now we will start to adjust our model. I will start by the second peak, which is B goes to C. I will click on it, and then I will start to adjust it. Now it's almost on the right position. Then I will back to the first one. And then we will increase the contribution of it. I will click optimize for the first one. Then I will select the second one, and I will click optimize. And now more or less our peaks are on the right position. And now we can scroll down under the model operation, and we can click optimize. So the first optimization, it was for each single step, but that one is for both steps, for the whole model. And then I will click on the all curves, and I will back again to the signal, and I will click on optimize. And here you can see that A squared is equal 0.9954, which is perfect, more than 0.995. So in this case, if we would like to get the kinetics parameters, that we can come back here and select the A goes to B. We can extract the whole kinetics parameters, activation energy, log exponential factor, reaction order, and contribution. And also after that, we can click on B goes to C, and we can extract all other kinetics parameters. Also, we have the possibility to click here to export the data as a text file. And then now we can go to do the prediction. So here I will just adjust the initial parameter. Instead of 100 minutes, I will do 300 minutes, which is 5 hours. And now we can see our curves. And for this prediction, as I said before, that this is important for us in order to do the validation, as most of the studies and industry is working in no isothermal. And then we would like to do only one isothermal in order to do the validation. After that, also we have the possibility to do the dynamic. Sometimes some customers have some limitation about the maximum heating rate. So in this case, from our side, we can do 70 K per minute in order, and then we can see how it will be our signal. Here we can show you the temperature program, and here we can click on auto zoom to see that the heating rate with the mass loss signal. Also, just to back again to our isothermal, that I forgot to mention for you, that here in the isothermal that we can also change from the signal to the conversion. And in this case, you will see that the conversion versus the time. After that, we have the possibility to go to the multi-step prediction. And we can click here on temperature program, and we can see that we have from 10 to 260, it was by 5K, and then from 260 to 500 by 2K. And also we can click add step, and we can do up to 900 by 0.5. And then we can do 900 to 1000 as isothermal 0 for 100 minutes. And now you can see your conversion with the new temperature program. And for example, here we can zoom, and we can tell you that, for example, in after 4.5 hours, your conversion is already reached 0.995. Back to the isothermal again, and I would like to show you about the concentration. As I told you that we are considering two reaction steps, A goes to B and B goes to C. So in this case, I will remove all curves and I will select only at 200 degrees C. So this is, we have A concentration. After that, we have B, and then we have C. Yes, just a second, maybe I will check for you. For 300, we have A, and we have B, and we have C. So here it's much clearer that you can see that the green one, which is A, that we have the concentration decreasing, while the concentration of B, the blue one, it's increasing. And at the end, finally, we can see here the product C, it starts here to increase. And now we can make it up to 500 or to 600. And then again, we can go to the 300, and we can see this is A, this is B, and this is C here. And one last thing, that we were speaking about the process optimization, that this is under this section, that we can click on the conversion rate, and we can click calculate, and now we can show the temperature program of us. That here I will just adjust here the heating rate between 0 and this. So we can see that when we have a conversion rate by 1% per minute, that we have the final match, it's ending around 107 minutes. And when we will decrease it to 0.5 per minute, that we can see it's almost double. The final match is around 203 minutes. And now I will back to my presentation. So this is a step-by-step recap. So as I said before, that we need a material for pyrolysis. It can be a biomass, rubber, or thermoplastics. And then we can do the measurement by TGA at different heating rates. The minimum is 3. But if the ask where is less than 0.995, so we can do more. And then the combination of TGA with Kinetics Neo, that we can do the Kinetics analysis. And then as output, we can get the Kinetics triplet, the prediction, and the process optimization. For the prediction, it will be nice from your side to select one of the isothermal in order to do the validation of our model. And up to now, we don't have any standards organization which we can follow. So that's why we are keeping to follow the ICTAC recommendation. And ICTAC, it's an international confederation of thermal analysis and calorimetry. And we were part of this nice publication or nice recommendation. It was done for the analysis of multi-step kinetics, as it's one of the main challenge in kinetics for pyrolysis. And then if you would like to get the Kinetics Neo software, that it's just, you need to go to kinetics.net.com and click on request trial version and fill out the form, and in few days or few hours you will receive the software. After that, as a second stage, that you can go to the learn section, and we have a clear guide with the screenshot step by step how to use the software. So the software, it's for 30 days, and during the 30 days that we can support you. So feel free to ask us, or if you find any problem or difficulty, just contact us back and we will help you. Our email is kinetics.neo@nets.com. Thank you for your attention. And now I will read your question aloud, and then I will reply to each one of them.